Okay, so torque and static equilibrium. So static equilibrium is a situation where the total torque on a system is zero and the total forces acting on the system is zero. In other words, the net torque and net force are zero. And it's not just the net torque about a particular reference. It is the net torque relative to all reference points. So any hypothetical reference point, you would have no torque. Um, if you have the situation where you have no net torque about any reference point, then the object is not going to start to rotate, right? Because, well, the torque is a rate at which that rotation is going to start building up. Um, so, um, just a recap, torque is equal to R cross F. This is the magnitude of torque, of course. And the magnitude of that is going to be the magnitude of the radius times the magnitude of the force times the sine of the angle between them. The radius is relative to a reference point, which we are going to call a pivot. Okay? And the pivot is just some point that you choose to say, hey, you better not be rotating about this point. So you pick a pivot, you then have a radius that emanates from that pivot, and you have forces that act on the object, which make certain angles with that radius. Just a reminder that torque, which is coming out of the page, is counterclockwise, and torque, which is going into the page, is clockwise in terms of its rotation. This would be a positive TZ and a negative TZ. And we are going to express things in terms of the Z component of the torque when we're working on it. So kind of the prototypical example is scaffolding with a man standing on it. And so I have the scaffolding with the mass capital N and a man with a mass little m. The scaffolding has a total length of L. We're assuming it's uniform. Because it's uniform, the center mass is at the midpoint of the scaffolding, and the force of gravity is going to be acting at that midpoint. The mass is a quarter of the length away from the left end. On the left end, we have string 1, and on the right end, we have string 2. These are like cables that are supporting the scaffolding, and they exert tension forces that point directly upwards. And the idea is to determine the unknown forces. The two unknown forces are force of tension 1 and force of tension 2. Now all the forces in this example are just straight vertical, and the scaffolding is straight horizontal. That's just to make the numbers work out nice and easy for this first example. What you would have done if you were working with Newton's laws is you'd work out the total force, the net force. And you would just go, okay, well, the total force in the y direction had better be 0, so that's going to be ft1 plus ft2 minus mg, right? The problem is there's two unknown variables there, but only one equation. So we can get a relationship between tension 1 and tension 2, but we wouldn't be able to actually solve for one or the other. And the resolution of this is torque, okay? So we might say, hey, the system's not accelerating in the y direction, but that doesn't mean it's not rotating about the z-axis, right? It could just be keeping its y elevation and start to rotate. And so the tension 1 and tension 2 are going to have to be balanced with each other in such a way that they don't produce a torque, right? Because if there was too much force in the right cable, it would start to rotate counterclockwise. If there's too much force in the left cable, it would start to rotate clockwise. The forces are equilibrated so that they don't cause rotations. So we're going to have to go use torque to generate equations. So whenever I want to compute torques, I have to have a pivot point. It's something that you specify when you're computing torques. So I place my pivot point on the far left end of the scaffolding, just as a starting point. Just as a tip, wherever you place the pivot point, you do not have to worry about the forces acting at that point because the radius will be 0, and therefore there will never be a contribution of torque from any force that is located at the pivot point. So usually it's a good idea to place the pivot point on a force that you do not know, one of your unknown variables. You don't have to, but that's kind of a good idea. Placing a pivot point on a force that you do know is a really bad idea. And placing it somewhere not special at all is just kind of a pain in the neck. So we're going to use a condition of static equilibrium to determine the unknown force. I've placed my pivot on the far left end of the scaffolding, and we have a chart here. And in the chart, I've put the radius of each force from that pivot point. So tension 1 has no distance from the pivot point. The man's weight is a quarter of the length of the scaffolding from the pivot point. The weight of the scaffolding itself is acting at the center, so that's at half the length of the scaffolding. And the other cable is a full length of the scaffolding away from the pivot point. And then I compute the torque. And the torque is always going to be either positive or negative, depending on the type of rotation that that force would create relative to the pivot point. So for instance, relative to the pivot point, force of tension 2 would create a counterclockwise rotation. And if you're not sure, just pick up your pencil and hold it at its left end and then push upwards on the right end, right? How's your pencil moving when you do that? It's rotating counterclockwise, isn't it? If you want to know about the weight, then hold your pencil at the left end and push down on it in the middle. That's clockwise rotation, right? The bookkeeping for these different directions of rotations is that counterclockwise rotations are positive and clockwise rotations are negative. So I have my torques with appropriate signs, positive and negative, depending on what type of rotation they produce. Now, technically, I could reverse that convention without screwing anything up. So I could say clockwise rotations are positive and counterclockwise rotations are negative, and all the math would still work out because I'm just trying to add these up to be zero. So as long as you're consistent, just stick with whatever convention makes sense for you, and you'll be fine. But counterclockwise and clockwise rotations always have to have opposite signs from each other, whatever the convention is. So my convention, counterclockwise is positive. So this came in with a positive torque, and then these two come in with negative torques. In each of these cases, the angle between the radius and the force is 90 degrees. It's like, for instance, here's a hypothetical radius or another radius or another radius. The radius is always parallel to the scaffolding, and all the forces are perpendicular to the scaffolding. So all my sine of thetas work out to equal just 1. And so I'm just left with radius times force with some particular sign in front. So I have my z components of torques. So all of these are computed from radius times force times sine of theta, positive or negative. Okay. And that is that. So now it's just a matter of balancing those torques. So the sum of the torques has to equal 0. And so I add them all up, and then I solve for f of t2. And I get the f of t2 is a quarter of the mass of the man plus half the mass of the scaffolding. Okay. All right. Now you can probably guess the ft1 had better pick up the other 3/4 of the man's mass and the other half of the mass of scaffolding, and that is correct. You can find that pretty quickly from Newton's law, but we're going to use static equilibrium to do it. And so what I'm going to do is I'm going to put my pivot point at the far right end of the scaffolding. All the same logic applies, but now you see that some of the forces now change the sign of their torques. So the weights now being to the left of the pivot point and pointing downwards would create a counterclockwise rotation now, right? Because this would tend to make a rotation like this. So the weight of the scaffolding and the weight of the man now have positive torques. Ft2 doesn't produce any torque because it's right on top of the pivot. And Ft1 produces a negative torque because this guy wants to make a rotation that looks like that, clockwise. So he gets a negative torque. Also, notice that the mass of the man, or the man's weight, is a distance of 0.75, 3/4 the length of the scaffolding instead of a quarter, right? Because this distance is 0.75 L. So he's further away. So he produces more torque on that pivot, or relative to that pivot. So, balance our torques and solve out the equation. We get Ft1 is half of mg plus 0.75 of mg. Big M for the 0.5 and little m for the 0.75. And then we can use Newton's law. In fact, we could have used it earlier. I kind of did when I made a prediction. I guess I can draw when I click. Better be careful about that. But I like to save Newton's law to, at least in simple cases, to check my math. Because, sometimes you're going to make a mistake with the torques, and it all has to hang together. So I know that the sum of the forces in the y direction are better equal 0. Now that I know them, I can go ahead and plug them in. And sure enough, it checks out that I get 0 equals 0. Torque can be used to understand levers and mechanical advantage. So here I have an example with a lever system. I have some downward force pointing down on the left, which is not known, and I have a 100 kilogram mass sitting on the other side of this seesaw, and it's 1 meter away from the pivot, the actual real pivot, and the force is a little bit further away, it's 1.5 meters away. And I can ask, okay, how much force does there need to be to support the mass, or to balance its weight? Well, there's 3 forces in this problem. There's the force that's pointing down on the left, there's the force from the 100 kilogram mass, and there's the force that little triangle exerts upwards on the seesaw to keep it from falling down. I'm going to call that the support force. I don't really need to see the picture with the triangle and the mass, so I'm going to draw what's called a rigid body diagram. And in this case, we just represent our extended object as just like a simple line or some simple figure. And we draw our forces sticking up off of that rigid body diagram with all the relevant angles and dimensions. And I'm going to put my pivot point on the support force because that's one that I don't care about and I don't know the value of. Right? So since I don't know the value of the support force, I don't really want to have to worry about it, so put the pivot point there. It won't enter into the calculation if I do that. Now I balance the torque, and so I have 1.5 meters for the unknown force, 0 meters for the support force, 1 meter for the force of gravity of the unknown mass. Work out the balancing of the torques, and I get an equation where I solve and find that the force is 653.3 newtons. Now, in particular, notice that it's 2/3 the weight of the mass, right? So I can support the mass using less force than the weight of the mass itself, okay? And that concept is related to what we've talked about in the past, which is mechanical advantage. So the output, which is the weight of the mass, over the input, which is the force I put into the system, the ratio of those is the mechanical advantage. And sometimes it's work out over work in, but we're going to just leave it at this for now. And in this particular case, I find, okay, I'd have the weight of the mass on the top, and on the bottom I have 2/3 the weight of the mass, so I get 1.5 times the output force for relative to the input force that I put in there. So this is, part of how we understand force is not something that's conserved, it's something that's balanced. And in particular, we can sometimes end up with these interesting situations where we put in a small number of newtons and support a large number of newtons. And what's going on is, we could technically probably lift that mass off the ground using a very light force, but the lighter the force is, the bigger the length of the seesaw is going to be. And so the real trade-off is that you're going to have to move that force through a larger distance, therefore doing more work in order to lift up the mass with less force. And that's kind of where torque and work, or torque and energy, are kind of related to each other. So next we have kind of an interesting situation. We have like a I don't know, maybe it's like a diving board. I don't know what this thing is. We have some vertical support. There's a horizontal beam extending off of it. The beam is attached to an opposing wall by a string or a cable, which exerts a tension force. But this joint here is in a string, which means it can exert forces in the x and the y direction. So I'm going to call that force 1, and I just have a kind of generic thing representing the x component of that force, and a generic thing representing the y component of that force. And that's basically how I'm going to do the bookkeeping for this thing. Also, I'm going to assume that this is uniform, so that the weight will act at the center. So here's my rigid body diagram. And I need to pick some pivot points. So I can put a pivot on the left and get these torques. And you can see the first time I don't have a sine of 90 degrees or a sine of 0 degrees. So when I put the pivot on the joint, the forces from the joint don't create any torques. And I get this balancing of my equations where I find that the tension is equal to the weight of the beam. Then I put my pivot on the right hand side, and now the tension doesn't produce any torque, but I get some torques from the other guys. Now the interesting thing is that the x component of the force from the joint doesn't contribute any torque. That's because it's parallel to the beam itself. So any forces like pointing directly at the pivot point, they won't produce torque. You have to have some angle relative to the pivot point to produce a torque. And so this guy's actually going to produce 0 torque, which means he's not going to enter into the calculation here, which is a bummer if we want to know what he is. So when I balance these equations, I can solve for F1y. If F1y times L minus mg L over 2 is equal to 0, so F1y must be half the weight. Now, and it says here again, F1x is parallel to the lever arm, so to solve for this, we either need to use a pivot not on the lever or use Newton's first law. So using Newton's first law to do with the balancing of forces, I can say, oh well, the forces in the x direction need to balance. So F1x plus Ft times cosine of 30 at better equals 0. So I get the negative of Ft cosine 30 for F1x. And you can just plug stuff in, and now we have the value of F1x. Now notice it's negative, and what that means is that in reality, that force isn't pointing to the right, it's actually pointing to the left, like this. Okay. Whenever you get a negative when you solve for a force, that always just means it points to the opposite of the direction that you thought. And then I was going to do a calculation with a pivot point out here. So I took a pivot point and put it, kind of in this direction, the same direction as the tension force, 30-degree angle, a distance L from the thing, just to show you that the pivot point doesn't have to exist on any particular object. Okay, it could just be out there in outer space. Okay. And kind of the problem was that just as I was working through it, the math was getting more and more complicated for computing the angles and the distances. And it's, it's doable, but it's kind of, as you can see, it's very involved. And then I got down to the end, and I realized I had the square root of a negative number. So I was just like, I don't care enough about demonstrating this to go through this again to find out where I made error. So, if you want to try and do that, here is my work, and there is a mistake somewhere here. I have no idea. It's pretty involved. So I'm guessing it's here where I did the law of cosines. I think I should have had a negative sign there, right here, because this is actually a negative number, or just made it positive cosine 30. But anyway, we shall see. But anyway, so you are free at your convenience to go ahead and work this out, but I am not going to do it. So I was going to show you that you didn't need Newton's law to get that last force, but just go ahead and use Nanosolve. Save some time. All right. Thank you very much.